right, so I forgot to start the recorder at the beginning of the video. So I will do a quick recap of what we did today.
Yes.
So we expect for certain systems that we would get complex eigenvalues. When we get complex eigenvalues, we also expect that we get complex eigenvectors. So I've gone through this system, found the eigenvalues in our typical way. We find our eigenvectors in the typical way. So here are our eigenvectors. We see that the eigenvectors are complex conjugates. The eigenvalues are complex conjugates. And we can write the solution in terms of those complex eigenvectors and our complex eigenvalues. Generally, we want to, well, we can, in general, our solutions are always going to be, our eigenvectors are going to be conjugates, complex conjugates of each other, and our eigenvalues are going to be complex conjugates. We want to write those in terms of real functions. So we use a superposition principle, some algebra, and we can show that we can write our system, our solutions in this way, where B1 and B2 are given by these expressions. I prefer B1 and B2 given by these expressions. So here's the calculations for the example we just did, using both ways. And we get our solution to our system. And if we write it as a general solution with our constants, we end up with this.
That was beautiful.
Okay.
It's efficient.
That was, yes.
You should post like a little 5-minute recap video at the end of every one. Like just like go through the notes real quick.
Yeah. That's not a terrible idea. I kind of like it.
Just like if you're past the real line, example number 2.
So here's our system for this example. So we want to solve, our first step always, solve determinant a minus lambda I equals 0. So we get 1 minus lambda negative 8, 1 negative 3 minus lambda. That determinant is 0. When we do that determinant, 1 minus lambda times negative 3 minus lambda plus 8 equals 0. So that becomes lambda squared plus 2 lambda plus 5 equals 0. Does it bother anyone else? It's just a little irksome that the numbers are first and the lambdas are subtracted. It kind of bothers me, just a little bit. Makes me think a little bit extra more. Use the quadratic formula, and we get lambda equals negative 1 plus or minus 2I. So there are complex conjugate eigenvalues. Now, for lambda equals negative 1 plus 2I, we solve our system of equations. So that's 1 minus lambda k1 minus 8 k2. That gives us 2 minus 2I k1 minus 8 k2 equals 0. And for our second equation, we get 1 k1 plus negative 2 minus 2I k2 equals 0. I use this equation. So k1 equals negative 2 minus 2I k2, which is 2 plus 2I k2. So I let k2 equal 1, and k1 then is 2 plus 2I. If you use the first row, your eigenvector will look a little different, but it's still a valid eigenvector. So k1 is 2 plus 2I1, which is 2, 1, times 2, 0, or sorry, plus I times 2, 0. And now I'm rethinking what I said before, Max, about that 0. I'm not sure that it might not always be 0. So the real part of K1 is 2, 1. The imaginary part of K1 is 2, 0. So this is B1, and this is B2 in the formula that we gave, or the form of the solution, if you want to think about it that way. So our solution is going to be C1 times 2, 1 cosine 2t minus 2, 0 sine 2t e to the minus t plus C2 times 2, 0 cosine 2t plus 2, 1 sine 2t e to the minus t. And if I write these as one matrix, I get C1, 2 cosine 2t minus 2 sine 2t. That's this top row here. The bottom row is just cosine 2t. E to the minus t plus C2. We get 2 cosine 2t plus 2 sine 2t. My bottom row is sine 2t times e to the minus t. And there's our solution. Let's look at the phase portrait of this one. So we have 1 here and negative 8. And 1 and negative 3. And there's our phase portrait for that one.
Looks like the milk.
Yeah, that's what I was gonna say.
So all of our solutions spiral towards the origin. So the origin is an attractor. And that comes from the e to the negative t term. We're going to get a negative exponential. And then those swirling bits are from those sines and cosines. If you think of parametric equations with sines and cosines and e to the negative t. Let's plot a bunch of those, and that's what we get. It's kind of a nice phase portrait. And I definitely like, I set my computer to dark mode. I like Wolfram Alpha in dark mode.
How much does Wolfram Alpha Premium cost? Oh, so much.
I do Wolfram Alpha Pro. I started doing that when I was in graduate school. I think it's like $50 a year.
Oh, that's not bad.
Yeah. So when you if you have an integral, you can click and it'll show you the full all step-by-step solution. I have tried. I've tried to get the school to pay for a subscription to Mathematica for our class. They won't do it. Yes.
Like ChatGPT has like a tutor
I got a reel on Instagram the other day. It was a kid asking his dad for help with his math homework. And dad says, "Dad, you're an engineer. You can help me with my math homework." And dad's like, "So what are you working on? Solving equations?" He said, "No, we're actually doing surface integrals in 3 dimensions. But I figured you could help me because you're an engineer. You know a lot of math." And the dad says, "Here, let me show you how to get a subscription to Chegg."
Yeah, I was always like, I'm like, I have no clue how to solve this. I'd search it out. Ooh, sweet. And then it's just paywall.
Yeah, I know.
It's so annoying. It's actually so annoying. Like, I'm not paying for a Chegg subscription.
So 51 and 56 have to do with the solutions to number 38 and 40. So that's why those even ones are pulled out of this set of odd problems.
37, 39. That's 4.
So we had